somewhere in Cuernavaca, right? And he will be here to talk to us about Riemannian versus Kahlerian normal coordinates. Thank you very much. Thank you very much for the invitation.
Bueno, muchas gracias por la invitación en esta bonita ciudad y en esta bonita conferencia. Acabo de escribir como las últimas 2 horas. ¿Ah? Oh, I should be speaking English. You know what? I do not even see the difference. I do not feel the difference in my head. Man. This is a problem. I'm sorry, if I should ever switch back to Spanish, then of course you just shout at me. Yeah. So, well, thank you very much for being in this very beautiful city of Mérida and this very beautiful conference. First of all, I have to excuse myself because the last 2 hours, or was 2 hours and a half, I spent writing this talk. So, which first of all meant I didn't catch up with the talks because for obvious reasons. They were, I think. They didn't merit it, so but I wasn't paying attention. And the other thing is, I hope I didn't make too many errors. So, in case I even forgot to write where I am. I'm in the Institute of Mathematics in Cuernavaca, as told Matthew. Now let's go ahead. I want to talk about first about Riemannian, or more precisely about affine normal coordinates, then about Kählerian normal coordinates, and some consistent equations which are related to 2 things, and eventually about Hermitian symmetric spaces. Let me just tell you beforehand that what I'm interested in is explicit formulas valid for arbitrary orders of differentiation. Yeah, I'm not really interested in what the first term is, the second term is, or whatever. Unluckily, it doesn't work so nicely. So in case you have expect some very beautiful formulas, very simple formulas here, then I'm disappointed as well. So, yeah, but at least there are some formulas which are possibly interesting. Yeah. So most of the things you can easily guess a little bit of formulas here of partial differential equations. You know that it should be true once you set up to find it. So, but the point is here to find explicit things. So let's go ahead. So what is Riemannian normal coordinates? Suppose we have an FR manifold, which is a manifold with a connection on the tension bundle. For Riemannian manifolds, they're always torsion-free. Some formulas they're more generally true for torsion. And it's more interesting to do the things with torsion at the same time. So then we can have at every point P, we can just think about the exponential map, which goes from the tension space here, from the tension space to the manifold, and it sends a tangent vector to the endpoint of the geodesic, the unique geodesic which starts in P and has tangent vector x in P. So this is exponential map. Then we can define, in order to describe the differential of the exponential map, this is one here. The problem is that it goes from there to there. But then we have like this canonical identification. This is a vector space. This is a tangent space of a vector space in a vector. So this is just the same vector space. And here we take the parallel transport along the radial geodesic, as I wrote there, and I take it inverse, so I get that there. So what I do end up with is for every tangent vector x, I get an anamorphism of the tangent space to itself, which is at least defined whether exponential map is well defined. Meaning if the manifold is complete, it's defined all of the tangent space. It's a smooth function on the tangent space with values and the anamorphisms of the tangent space. So, if this always it is defined and it is invertible for a neighbor of 0, at least, it may not be defined everywhere. This is like related to what is called conjugated points, and its forward is in case it is invertible, I will denote its inverse by evidently this way. Yeah? So it's a pointwise inverse of this. And of course, at one point or other, we'll think about power series. So I will take the Taylor series of those in 0. Yeah, and so this will be the formally invertible inverse of this power series. So now let's define some special power series. So we take the iterated covariant derivative of the curvature tensor. So, and defined in this way. So this gives us a power series, because we have infinite terms, a power series on the tension space with values in the endomorphisms, which is defined this way. I can do this at every point. So what this really is this is a section of a power series bundle. Yeah, but I do not worry too much about whether it's infinite dimensional, because it doesn't really matter. Yeah, so at every point of this power series, the same thing is this is the torsion. Yeah, I do the same thing with the torsion. Again, I get a power series with the endomorphisms of the tension space. Moreover, I let the n be the number operator on power series. What is the number operator? A number operator multiplies the power, each term in a power series by a number of x's which occurs. Yeah. So, for example, here this has r plus 2 x's. So the number operator would multiply this by r plus 2. Yeah, and this for all of the sum. And this one here has r plus 1 x's, and so it would multiply by r plus 1. So, and then we have this following thing. The parallel transport, I call this parallel transport equation, which means that the backward parallel transport, which describes the exponential, the differential of the exponential map, satisfies this formal differential equation. It's only formal because you can easily solve it. Yeah, it's extremely easily solvable. And what this means is essentially that, well, this is why I wanted to be torsion here as well, because this term got me in more trouble. So what this means is that you can define the Taylor series of a parallel tensor in normal coordinates is completely determined by by this phi inverse. This phi inverse determines the Taylor series of every parallel transport in normal coordinates, and this means that you can easily find the Taylor series of phi inverse, and so this means that you can easily find the Taylor series of an arbitrary parallel tensor in normal coordinates. Yeah. For one you easily get from this. By the way, how do you prove this? How do you prove this? Man, I'm not sure how other people. I think I'm the first one to write this down. But in my habilitation thesis, I solved this for the case that t is 0, that the torsion-free case. And I did this, I suppose, like other people have done before. You write down a recursion relation, and you solve it. And at the end of finding the full power series of phi inverse, you by miracle you find out that it satisfies this equation. Yeah, it sounds like a miracle, but it's only after doing all these calculations that you eventually find out it satisfies this equation. Yeah, this is without the t. Then a couple of years ago, I did the same thing in the case of if r is 0, the curvature is 0. Yeah, I did exactly the same thing. I did write up some recursion equations, and I found out that it by miracle satisfies this equation. When the n cancels essentially. Yeah, if r is 0, the n essentially cancels. And they found out that it satisfies this equation. Yeah, but luckily, in the meantime, I'd found out a very neat way to prove this equation. And this is, I really like a Cartan thing. So what this equation really is, it is a obstruction, or it is, if you write this way, like this term minus this term is equal to 0, then this means that the obstruction vanishes against the existence of a Jacobi fields. Now, Jacobi fields are solutions to an ordinary differential equation. So this has no obstruction at all. But if you ask that something is a Jacobi field along every radial geodesic, this is a partial differential equation. And this has obstructions. Yeah? And if you write down what the obstruction is, you find out exactly it's the difference between two sides. But you know that in exponential coordinates, you have plenty of Jacobi fields. You have plenty of vector fields which along every radial geodesic are Jacobi fields. You just take the rotations, the rigid rotations. Yeah? The linear vector fields. They're all Jacobi fields along arbitrary geodesics. And so this is sufficient to prove that this equation has to be hold true. I think it's a really nice proof. So it's possibly the only thing which is not surprising. It is not completely obvious how to prove for the main people in the audience. So let's go back to Kählerian normal coordinates. Well, first of all, the Kähler manifold is a Riemannian manifold together with an almost complex structure. This is normal complex structure, which is parallel with vector Levy-Jevio connection nabla. So this is orthogonal, and this is parallel with respect to I. So I write almost complex, although this not really makes a problem, because the theorem of Nielen and Nierenberg, a famous one, tells you that an almost complex structure is integrable in the sense that it has a homomorphic atlas. This is a complex manifold, if and only if there exists a torsion-free connection making I parallel. So if I already require this to be 0 for the torsion-free null DFG connection, it's automatically integrable. So I could skip this almost there if you want. So yeah. So the remark of Bochner now is missing something here. I tried to correct it, but I couldn't because my computer is really like not working properly. Despite being the nicest coordinates for general Riemannian manifold, the Riemannian normal coordinates entering the point of Kähler manifold are not holomorphic. This is what's missing. They are not holomorphic coordinates. What could this possibly mean is M is a holomorphic manifold, and this is a complex vector space. Yeah, it's a complex vector space by I. I only write it with big I, not with small I, but it's nevertheless a complex vector space, so it's automatically a complex manifold. Yeah, it's a real tangent space. Normally you ask for the complex space. Yeah, you just watch out. Yeah, so this is a real tangent space, but nevertheless it's a complex manifold. And I asked this to be a holomorphic map in this sense. It's not. Yeah, at least it's not in general. This is yeah. I'm not because of. It's just another slice. How would you possibly extend this? Sorry?
It's only half of the complexity.
Yes, so the first thing is you would have to continue analytic. So something like this, but then, yeah. So, did I get everything? What? Okay, so that's another definition is classically as a Kähler form. It evidently determines the Riemannian metric. And so this gives me a chance to define what a local potential is. A local potential function is a local function which is a preimage of omega in the sense of the del bar lemma. The del bar lemma says that if you have a form which is del exact and del bar exact, then it has a preimage. It's like a del bar preimage. This is a del bar lemma. Now it's easy to see that omega is closed. So it's in particular, and it's 1, and so it's del closed and del bar closed. This means it's locally del exact and del bar exact, and for this reason, this only has local preimage like this form. Yeah. So the local existence of this is guaranteed by the del bar lemma. So what I'm not missing is here what the relation is. But the factor here is nice to have inside. Yeah. Because then otherwise, if you do not have the factor, then you get potentials which are not so obvious. So okay, so let's go. So the potential is not very unique. You can always add a real part of a local holomorphic function. Why? Because the holomorphic function is the kernel of del bar. Yeah, and its conjugate part is in the kernel of del. So this is why you can always add this. And so now let's make a definition. So an anchored local coordinates as an anchored local coordinate system is mapped from tangent space to M, which sends a 0 in the tangent space to the point, and its differential there is the identity. Yeah, so this is this is a characterization of exponential map. This is a very weak characterization of exponential map. It satisfies this. Yeah. I came up with this definition when I thought about making a nice definition of writing the Z spaces, affine spaces over vector bundles. Yeah, if you really want to give a definition, then you have to need anchored coordinates, the concept, and it works. Yeah, because you fix the differential, and in Z spaces you have to put more differentials, differentiate, but you only differentiate once the differential of the coordinates. So these are fixed by being anchored. Yeah, so this is the reason why if you want to write the jet bundles, FFN bundles over other jet bundles, it's very nice to use anchored coordinates. So, and now it comes to the main theme, which is not my theme, I don't know. So it's very simple proof. Possibly it's even Bochner, yeah, in the article where he showed that X is not holomorphic. Yeah. So in every point P there exists a new anchored holomorphic coordinate system from here to there, and a unique local potential function that the detail series satisfies the congruence, that this potential is equal to the metric, the square norm of the metric, modular power series of at least a quadratic in the holomorphic and holomorphic coordinates. Well, I would possibly have to give a rather big definition of what this means, but if you think about the polynomials on TPM, yeah, there are those which are complex polynomials or real parts of complex polynomials, yeah, and then are real parts of anti-complex polynomials, yeah, and there's something in between. Yeah. So so this means if you write a polynomial in TPM, you can write as a real part of the holomorphic coordinates or complex coordinates and its conjugates. Yeah, and depending on how many of those appear, you can say that the power series is at least quadratic in the holomorphic and anti-holomorphic coordinates. And there's better ways to prove it, but they're not easier to comprehend. So it's possibly the nicest way to put it. Okay, so I write that the domain is TPM, although it's in general it won't be. Yeah, it's only for simplicity. Yeah, it's like this talking about exponential or many maps and non-complete Riemannian manifolds. Yeah, so do not bother too much about this. So now let's come to consistency equations. I define the difference element to be the power series on TPM with values in TPM, which are at every point which gives me something like a diffeomorphism, so, and this way. So it should be the value of k in the point P. This gives in Sim and the power series on TPM with values in TPM, which is defined to be this decomposition. And as both are anchored local coordinates, we find that this congruence holds true. Yeah, it's differential of k in the origin. It's the identity. So this is what's written here. Yeah? So moreover, it has a well-defined composition inverse, which is just this. So let's see. The lemma is, which is essentially if you make up a rather complicated proof of the theorem that existence and uniqueness of the Kähler normalicals. By the way, the uniqueness normally is stated only up to unitary transformations. Yeah. The fun thing about making it anchored is that the uniqueness is unique. It's true uniqueness. Yeah. You just mod this out. Yeah. The ambiguity by just asking it to be anchored. Yeah. So so if you write this, we have like it's a composition polynomial complex structure. Yeah. And this is universal. This power series is universal. This means that the coefficients here do not depend on the Kähler manifold. Yeah? And as I told you, this comes about if you make a more complicated version of the proof of uniqueness, of existence and uniqueness. I'm not sure what you call this. Can calculate, but I was rather glad when I first calculated the 1 minus 1 over 12 there. Yeah. But in the meantime, I found ways to make this much faster. So suppose you're interested in doing this. So what can I tell about this kx? So the one way to calculate it is, I think this is the fastest way for me as of now. I'm not sure whether I ever find a faster formula, but this is the fastest I've come up with in the meantime, is the following. You do not write a differential equation for k, but for k inverse. So what is, you apply the number operator, yes, and this is the derivative of I in all the arguments. So you go all through all the arguments and multiply them by I in turn, in sum, and you multiply the result by I as well. And so this is a first order differential operator, and what the result is as this expression here, where you do the same thing essentially with a phi, which is a forward parallel back transport, the inverse of the one which has a nice differential equation. So why is this a nice equation? In some sense, because its identity minus phi is at least quadratic in x. It starts with this term here. This term here this at it minus phi starts with 1 over 6 rxyx. Right? So at least quadratic in x. So what this means is that you can solve this equation recursively to get the full expansion of k. Yeah, because if you have already found the terms up to order 10, for example, of k inverse, then you can write down all the terms of order up to k 12 in this expression, because this is at least quadratic, and then you solve this equation for the terms of order 11 and 12. Yeah? So this works this way. I'm not sure whether anyone has any other idea how to calculate this. Yeah, but this essentially gives a concrete way to calculate this. You know? All this has been expanded essentially in this way. So one corollary of this lemma is which are not, it's completely obvious that you believe that it's true, but if you really want to prove this, I'm not sure how you really do this. Yeah. So this means that if you have a totally geodesic Kähler submanifold, yeah, then the restriction of the Kähler normal coordinates to the tangent is this. Yeah? I mean, it's obvious that the normal potential restricted to the image of the tangent space would satisfy the congruence, but you do not know that the image of the tangent space is equal to the submanifold. Yeah? Because we are not in exponential coordinates. In exponential coordinates, the image of the sub-tangent space would be the submanifold. Yeah? So here's something like in limbo what you're really doing. Yeah? But once you have this lemma, or whenever you prove it, it's obvious because if the total geodesic, all these endomorphisms will map the submanifold to itself. Yeah, so this K maps the submanifold to itself. This means that the image of the Kähler normal coordinates restricted to the subtangent space will be the submanifold, and then you find out that the potential satisfies the congruence. This is proved. Yeah. Well, so now it's almost done. So I want to say that the normal potential is you can calculate as well from the difference element. So once you have that the difference element is a universal polynomial, composition polynomial, the curvature tensor and all the covariant derivatives, and the I, then you find that this one here is as well, because you just write it this way. This essentially is the differential of the Kähler normal coordinates. I can write it differently, but then you find out that the normal potential satisfies this equation. Yeah, and so this means that it's always it's the same as the composition polynomial, the curvature tensor, and all its covariant derivatives. Blah blah blah. See? Fine. The remaining distance function as well. The remaining distance function satisfies this one here. Yeah. So this is essentially because in exponential coordinates, it's a radial isometry. You just write down the definition and you got this. So, and let's go to Hermitian symmetric spaces. So the Hermitian symmetric space is a manifold where the curvature is covariant parallel. Then you can show that there exists a set 2 graded algebra bundle GM such that on the manifold M, on this local Hermitian symmetric space, which has this set 2 decomposition. These are the even part, this is the odd part. And in this Lie algebra, it is true that this is the curvature tensor is encoded in the bracket here. This is the only thing you need, yeah, at least at this point. Yeah. So, of course, there's a beautiful classification of local Hermitian symmetric spaces, essentially due by Cartan. Yeah. But I want to mention that all this construction works as well in the pseudo-Kähler case. Yeah. You can do pseudo-Kähler symmetric space here as well. It doesn't make any difference. Yeah. So, and then the lemma is that the difference elements are given by these power series. Yeah. This did cost me quite some time to find out. It's not that straightforward as I would have thought. I'm sorry. I first did this in the Grassmannian. I calculated the difference element for the Grassmannian, which is like the obvious example, the complex Grassmannian. And you find out the Taylor series is very similar, but it's not written in terms of the curvature. And then what I did is I did the same thing for the twistor spaces. This cost me a lot of time. No, the twistor spaces, sorry, the real Grassmannians. The real Grassmannians of oriented 2 planes, which is like the very accurate example of a Hermitian symmetric space. Yeah? And you find out that miraculously, if you calculate, for example, the potential, it looks very different, but you get the same potential here. So once I got this for the Grassmannian of the oriented 2 planes, I was convinced that the formula is true for arbitrary spaces, but then it was still some time to prove it. So this is a potential. Yeah? This is a potential here. Thank you very much. And happy birthday, Adolfo.
One of the main things which I did not write down is
so it's the following: that one of the conclusions here is that you have at least three different objects which gives you this the full geometry of a Kähler manifold. One is a normal potential. If you know it at one point, essentially you know the manifold by analytic continuation. Yeah? Nobody knows how to do this, but at least theoretically you know the Kähler manifold by analytic continuation once you know the Kähler potential, the expansion of the Kähler potential in one unique point. The other thing is you take the iterated covariant derivative of the curvature tensor plug in x's and ix's as many as you can so that you get a polynomial, and you do make this a power series. So this contains the same information as a Kähler potential. This is obvious, more or less, but the fun thing is how to write equations really explicitly to relate the twos, which I do not have, but I have reasonable equation which makes use this way. And the other thing which is somewhat a surprise is if you take the distance function in Kähler normal coordinates, yeah, this contains the same information. Yeah, if you write the distance function in Kähler normal coordinates, it contains exactly the same information as the covariant derivative of curvature and the local potential. Yeah, so I didn't have time to write it. So. Sorry.
It would have been great to curvature, whatever, written down exponential number coordinates, just to if the thing goes to just looking at it as a suspect. Okay, let's see.
Next time, yes.
I have computer programs does quite a lot of things very nicely, but the real problem is there that you do not know how to apply the simplifications. How many simplifications do you have? For example, these formulas I told you, which are not so. This one. And add square on every unit for me.
It turns out that it's very easy because you know that it's true. But that's where x and that's why x.
More questions?
Yeah. I think I've seen something similar in consciousness called progressive geometry and symmetric systems. I can't say exactly. I should have said. So the point is, I really was interested in relating the potential and the. But there are other forms which are good to take arc sign, or the tension of a harmonic sign, but I should look it up, yeah.